Okay, so thanks for the invitation. I've been struggling during the week to know how to approach this talk, given it's like the last talk on a Friday evening around 7 p.m. And I thought the best would be to first acknowledge that gravity has been beating me up twice as much recently, because I rock climb, but I'm also getting older. So I thought it would be a good chance to actually bully gravity a little bit and remind us of why gravity seems to be so different than other interactions and other quantum fields. As I said, let me start by acknowledging that it is quite hard to be giving a last talk during a long day. So hopefully, after reading this paper during this week about why people nod off during talks, I probably learned a little bit of how to avoid losing my audience. But anyways, so before I start, I'd like to acknowledge that pretty much all the things I'm discussing here, they came about within this collaboration that we started roughly a year ago. We are 7 different researchers spread in Europe, also Eugenia, she's in the States. And throughout the year, we've been meeting every week or so to actually discuss papers on the foundations of quantum mechanics and gravity. And after more or less of a year of reading those papers and thinking considerably about the nature of gravity, today I'd like to briefly step back and have a more philosophy of physics kind of style talk where we're going to analyze closely where gravity seems to be so different, and perhaps like using that to guide us into the future when we try to talk about quantum gravity and relativistic quantum information. So here I have a brief summary of the main points that I'm going to cover. We're going to see that there are 2 different kinds of universality that gravity introduces or presents to us that we have to bear in mind. Gravity also introduced a direct notion of operational measurement limitation, which leads to the idea that we don't have no local gauge invariance observables in quantum gravity. And we're going to also revisit that later in the context of how do we even talk about quantum gravitational subsystems. And finally, in the middle of the talk, I'm going to also briefly mention the holographic principle and the kind of conclusions that some people have been trying to derive by the fact that actually we have this particular scaling between area and entropy in gravitational systems. Okay, so let's go into it. So the first one, everyone here learns even in high school to some extent. We know that gravity is universal in scope. It seems to affect pretty much everything that there is out there in the universe. But not only that, we also learn that gravity actually has a universal strength, which in our modern theories is implemented through a minimal coupling with all the other possible quantum classical fields. And the physical picture comes about through the equivalence principle, as you know. Now the question is this singular to gravity or not? And this has been already observed many years ago by Feynman, that actually there are other situations in which we seem to have an universal kind of interaction. So in Feynman lectures, you find Feynman saying that the fact that universal attraction might remind us of the situation in molecular physics. We know that all molecules attract one another by a force which, at long distances, and so let's keep that in mind for later, goes like 1/r to the power of 6. These we understand in terms of dipole moments, which are induced by fluctuations in the charge distribution of molecules, and so on and so forth. And of course, then he relates that, or he speculates that maybe what happens in gravity, that we have this attraction which is also universal, could be due to similar fluctuation in something. We just don't quite know that yet. So out of this slide here, let's remind, we have a kind of universality that appears in molecular physics at long distances. Okay, let's move on. There's another thing which is peculiar about gravity. As we know, we seem to live mostly across the visible spectrum. And as we've been discussing throughout the day, if you actually want to analyze smaller and smaller subsystems, you have to increase the frequency of your probe. But we know that in principle, before gravity, we could do that all the way to the smallest possible scales without any particular limit. But as soon as we have gravity on, we know that once you have the energy being too high, at some point you're going to reach a barrier in which you don't have any more operationally access to the smallest scales in space-time. So from an operational point of view, it already seems that space-time cannot quite be fundamental. at least in the sense that we won't ever be able to observe what's beyond the Planck scale, either in time or in space. Okay, so now for us to continue our journey, let's forget a little bit about our weirdo, gravity, and reminds us about the normal kids, the other quantum fields that we have in nature. When we do quantum mechanics, in principle, there are two infinities that we tacitly assume, even though in practice we cannot do anything about them. Well, the first one is that because quantum mechanics seems to be intrinsically probabilistic, in principle to derive probability distributions, you'd have to repeat experiments an infinite amount of time. Of course, we don't do that. And so intrinsic to any measurement or any distribution in quantum mechanics, there is some uncertainty around the accuracy of our probability distributions, which scales roughly as 1 over square root of the size of the system, the quantum system. There's another kind of infinity, which has to do with the fact that in principle, if I want to measure anything with apparatus, and I want to use apparatus as a recorder for that information, for every decimal case of your G factor of your electron, for instance, you need to have another factor in Hilbert space to record that information. And of course, we do not have that. And so in principle, actually, there is another scaling, another intrinsic error to any measure, which scales as e to the minus dimensionality of the Hilbert system of the apparatus. And in general, of course, we can ignore that, in particular because this error is way bigger than the second one. So as I said, those two things are always there, tacitly, but in practice, it doesn't quite matter. Because we know that within the formalism of quantum mechanics, without gravity, in principle, we could keep pushing and creating systems which are always bigger and keep repeating the experiments. Okay, let's bring gravity on again. Well, there is a problem here, especially with the second kind of infinity that wasn't so relevant in quantum mechanics without gravity. Because as soon as we try to make our apparatus bigger and bigger, to try to make a precise measurement, a sharp measurement, at some point, again, we reach a limit in which our whole lab would collapse to a black hole. And in fact, we know how to measure the entropy of a black hole, and so we know that that error that appeared there as e to the minus n, if in fact we were to arrive at our lab almost at the size of the black hole, that error actually scales with e to the minus a over g, where a is the size of the black hole. And so from that very heuristical point of view, we already kind of like have a feeling of why there is no precise observable, sharp observables that can be associated with any measurement whenever gravity is actually on. Well, unless we can do something else. Well, imagine that instead, as we try to make our sharp measurement of whatever quantum mechanical with gravity phenomenon, we keep increasing the size of the lab, but like throwing the lab all the way to infinity. So we never really reach the density in which a black hole would be formed. But you can imagine what's going to happen now, right? You have to keep increasing the size, and you have to keep expanding the size of your lab, expanding it all the way to the boundary of your space-time, to infinity. And so in principle, now you also understand why there is no notion of local sharp observable that can be associated with any gravitational quantum mechanical measurement. And so really, at the end of the day, we kind of like understand that the only sharp observables in any theory of quantum gravity should be the ones that are going to be recovered at the boundary, not the ones that are going to be defined locally. And to some extent, kind of like anticipating maybe all the problems with quantum gravity, this is exactly what the program of matrix theory and scattering theory is actually doing. All the observables in scatterings are defined asymptotically in the infinity. And then, of course, the question is, can we then rely on this quantum field theory approach where we're based in asymmetrics ideas to actually account for gravity? And we're going to come back to that towards the end of the talk. Let's again go back to our normal quantum fields, our normal kids. And we see some very peculiar things that were found out already by Srinicki in 9.3. Which is the fact that whenever you think about holography, you usually think about gravity, but actually that has been present in normal quantum mechanics and quantum field theory way before we start talking about the holographic principle. And here the idea has to do with the fact that if you go and compute the von Neumann entropy of quantum fields associated with any compact region of space-time, we do observe that there is a scaling of the entropy with the area of your compact surface. And this is like pretty much actually universal and also independent of the state, because when we zoom in, any state looks anyways as a ground state. And the calculation was done for the ground state. And so the picture that people usually have is that actually you have an infinite amount of modes inside the region and outside, which are entangled anyways, and they share the boundary of it. And so that's why the scaling would be naturally coming with the boundary of all the UV modes that are coming across the two sides of your compact space. As I said, let's bear in mind that this was proved to be the case for the ground state. And this, again, is not about gravity, right? And so we have this scaling law, and the finite part scales with the area. Of course, this is already in stark contrast to what we know about classical thermodynamics, where the entropy of any region can scale with the volume, and it can go all the way to infinity. You just keep exciting the states inside that region all the way as much as you want. All right, so now let's again oppose this to what happens in gravity. Well, in gravity, we have something called the holographic principle, which upper bounds the amount of entropy that you can contain inside any particular compact region of space-time. And in particular, this is the formulation in which you write the holographic principle, or the bound for the entropy, by using light sheets which are shoot out of your compact surface. And so this is actually a covariant way of writing this bound, even though initially people were relying on a spatial hypersurface and a non-covariant description of the relationship between the entropy and the bound. This is mostly work by Bosso. Now, remember for Zreniki and quantum mechanics, that calculation was for the ground state. But black holes are not quite ground state. In fact, we know that from the generalized second law of thermodynamics, if you do have a black hole associated with a compact region of space-time, it has to be the highest entropic state associated with that region. And in fact, the black holes are going to be saturating what we call the Bekenstein bound. And usually the bound, of course, can be unlimited, but for the black hole in particular, because of connection between the characteristic length of the black hole and the energy, that relation is saturated at a finite entropy. And now if you think that there is a quantum description of the black hole, because it is a system which has the maximum amount of entropy, quantum mechanically, you would see that the dimensionality of the Hilbert space associated with that particular compact region of space-time is going to scale with the entropy. But we know and we just agree that the entropy associated with that particular region is actually finite. And so you'd infer from that the dimensionality of the Hilbert space associated with that space-time region has to be finite. And so you'd be led to believe that whatever quantum mechanical description we're going to associate with that space-time region, it quite cannot be a QFT. Because for a QFT, for any quantum field, for any mode of a quantum field, we have basically a harmonic oscillator, which has a Hilbert space which is infinite dimensional, even if you have IR and UV cutoffs. And so that seems to be quite a stark conclusion. And of course, we can talk about that later, if this follows or not. But this is an argument that was proposed by Bau, Caron, and Sein a few years ago. Okay, there is another thing about the holographic principle that has been used in the past few years, and that comes in this paper by Jacobson in 2015, where by postulating that actually for any causal diamond in your space-time, that the change in entanglement entropy of this causal diamond can be divided in the IR and UV sector, and the UV sector is what he's going to associate with the geometry, and is going to be scaling with our holographic scaling. He was able to rederive Einstein's equation. Now, what's peculiar about that is the fact that we have now our scaling here, and this is a universal, in the sense that it was fundamental for his derivation of Einstein's equation that this scaling would be a constant, which is not the case if you go back to this paper by Zreniki. When you compute for quantum mechanical theories, you see that actually the scaling depends not only on the size of the region, but also the energy in which we're considering the system to be embedded in. And so you see that the universality of gravity here seems to be quite different to the universality presented in normal quantum fields when you compute the entanglement entropy for them. And again, for Zreniki, the calculation was in the ground state, and here we're imposing this for the EUV part of the theory. So it's the EUV that's being universal, which is quite peculiar. Now we go back again to our normal kids and our quantum fields. And there is one thing that somehow is always lurking in, especially throughout the whole day in all the talks that we have given so far, which is how do we even talk about quantum mechanical systems, subsystems, in particular in the context where gravity is turned on. Quite typically, to talk about a notion of subsystem in which we think that there is a Hilbert space which seems to be localized in some region of space-time, in quantum mechanics that's somehow quite trivial, as long as you have an algebra of observables which is given by the bound operators that can act in a Hilbert space. And this algebra is typically called a type 1 von Neumann algebra, which in the canonical examples that we can have in mind is whenever you have a separable Hilbert space. Then we have a very well-defined notion of subsystem. And that's why we go about writing tensor factors, so on and so forth, when you do normal quantum mechanics. Do we have anything like that in quantum field theory? Well, not quite. In fact, in quantum field theory, to have a notion of subsystem, which here we're going to represent it or instantiate it by thinking that whatever measurements and state preparations that we want to have in our labs, they can be carried out independently. You need to rely on two different properties. One is our microcausality, Einstein separability, that in whatever part of the different subsystems we can act over operators which commute among themselves if the systems are space-like. And there is also the property of the split property that I won't go into details of, but my point is going to be to show that even though this works in normal QFT, and we can actually implement or recover those two properties or consistently impose them, for gravity there is debate if the split property is valid. But I won't even go there. I'm going to show that already the first property becomes an issue when we want to talk about quantum gravitational systems. So let's understand what's going on. To understand, let's just look to QED coupled with a scalar field. So it's very simple. We can write our Lagrangian. We know that the Lagrangian is locally gauge invariant as long as the gauge field and our scalar field transform in that particular way. And that's pretty good. Of course, then we can impose that for space-like regions, our scalar observables, they commute. But now we have an issue, because we have a gauge symmetry or a gauge transformation of the scalar field in our theory. So even though this can be true, this is not gauge invariant. And so the question is, can we find a gauge invariant observable associated with the scalar field such that it's going to be also local in the sense that's going to satisfy some relationship like that? And in fact, there is a way, and those are called Drest operators. And you can, for instance, for this particular theory, you can write down this operator, which pretty much you can think of this whole integration here as if you have now one charged phi particle here and another phi particle here with the opposite charge, and connecting them both, you have a string of this U1 field, if you wish. And so once you do that, you can show that this operator, as long as x and y and z and w are defining two different operators which are space-like, then they're going to commute as well, and you have local gauge invariant observables. So that's good. And this can be done for all the fields that we know in QFT. But what about our weird kiddo, gravity? So let's try the same with gravity. Let's write a normal scalar field coupled with gravity. Once again, now gravity at the linear level has some gauge symmetry. Let's consider only linear diffs. We have our symmetry here. Our scalar field also transforms. Here already canonically normalized our metric perturbation. Once again, I can impose my scalar field to be commuting at space-like regions. But once again, we have the problem that that's going to be not gauge invariant. Can we recover something that's going to be gauge invariant and satisfies the relationship? Well, it turns out that you cannot. You can actually find gauge invariant Drest operators, but once you do that, and basically what you do, you have this particular way of transforming your operator and dressing it with this particular functional of the metric over there. Once you do that, and you can, there are many examples and many prescriptions to do that, you can arrive at a gauge invariant operator, but that won't satisfy anymore the notion of microcausality. And so that's very concerning.
What's the main reason for that?
Sorry?
What is the main reason why?
Maybe we can come back to that at the end for the questions. But we have this issue. And again, this was our prescription to talk about subsystems, to talk about experiments, to go into the lab and defining, I have a system A and I have a system B there. And here, this is breaking apart completely even for the level of linear diffs. So basically, we have our algebraic approach is obstructed in gravity. Because as I said, this dress operator, even though it's gauge invariant, it won't commute with itself in space-like regions. And intuitively, the reason why this is happening really has to do with the fact that in gravity, we don't have positive and negative charges. So you cannot really screen off your gravitational field. And basically, the main difference between this integration and the previous one is that this goes all the way to infinity, while the previous one was actually contained in an extended compact region in space-time. And fundamental to the argument was that even though I wrote Einstein and Hilbert, the only symmetry that I relied on was linear diff. So it doesn't matter really what kind of gravitational theory you're talking about. As long as you have linear diffs as your gauge symmetry, you're going to run into this kind of problem. So basically concluding my talk, now what? And that's I'm here to pose this for you. I would say that perhaps there are hints here on this kind of understanding to update our directions in relativistic quantum information and the kind of things or problems that we should maybe be trying to address and think of. I think there are direct implications for the understanding interpretation of GIE experiments and the whole notion of not only relying on the fact that you can write down subsystems in quantum gravitational experiments that are separated, but even stronger, to write down a cat for our gravitational systems. I'm not sure to which extent everything that I argued here so far would allow you to even consider that. Just want to observe that back to the argument about holography and the fact that we shouldn't think of gravity as a QFT. If everything is locally finite dimensional, in principle, all those problems go away. And so maybe one opportunity is to try to develop and think of gravitational phenomena in quantum mechanics representing a finite dimensional Hilbert space. Just want to highlight that Feynman's universality appear on the IR, while gravity a la Jacobson appear in the UV. And similarly, Cyrenaitis calculation is for the ground state for the holographic relationship, while for gravity is for the maximally entropic state for a compact region spacetime. So it seems that there is this opposite happening between the normal quantum fields and gravity. What is that trying to tell us? And maybe all those things are hinting towards something which might be a strong departure from our classic intuition about spacetime. I ran out of time, so I apologize for that. But basically, the message that I would say is that perhaps we should really try to knit our spacetime by really trying to recover that from only quantum mechanics and not having spacetime as a fundamental entity in our ontology anymore. And I stop here. Thank you.